we proposed the recurrent homography estimation using homography-guided image warping in focus transformer, namely RHWF. Homography estimation aims to find the global perspective transform between two images. It serves as a crucial step in a widely range of computer vision tasks such as image stitching, video stabilization, SLAM, and planar object tracking. The main motivation of our work is to further improve the recurrent homography estimation accuracy in a simple yet effective manner. For warping strategies, different from the previous work which acquire the transformation equivariance by pre-warping the input image, which are redundant in computation, we use the homography-guided image warping to improve feature consistency during recurrence. For attention strategies, unlike the attention mechanism in previous works that is pure global or local, we propose the focus attention mechanism which can gradually clarify the attention targets. This figure illustrates the architecture of RHWF. The homography-guided image warping and the attention focusing mechanism in focus former are arranged in an interleaved manner, which are appropriately absorbed into the recurrent framework. We note that the whole network is tied despite the number of iteration, which means the framework won't raise the network parameters. We employ convolutional neural network with residual connections as our backbone. After each iteration, we warp the image be guided by the present estimated homography to improve the feature consistency of FA and FB. The core architecture of RHWF is our focus former that achieves recurrent residual homography estimation. Focus former mainly contains two parts that accomplish attention mechanism and homography estimation. The attention module captures the inter-correspondence of the input image pair. The homography aggregator module decodes the correlation within local areas to obtain the residual homography. The performance of our proposed RHWF can be further improved by multi-scale refinement. Now, we illustrate the network details of our RHWF. The left part of the slide demonstrates the correlation pooling operation of focus former. Before being sent into the homography aggregator, the correlation volume is separately processed by average pooling and center sampling in the last two dimensions to produce two feature maps, then they are reshaped and concatenated in the channel dimension. This operation keeps the perceptual range while saving the network parameters by reducing the input channel of the feature maps by nearly a half. The right part of the slide shows the detailed architecture of the CNN backbone and the homography aggregator in focus former. In A, the solid lines denote the branch for extracting the feature map of one scale RHWF, and the dashed lines of the additional scale in two scale RHWF. The numbers denote the depth of convolution layers. In B, D denotes the depth of convolution layers, which is set to D equals 80 for one scale RHWF and D equals 64 for the extra scale in two scale RHWF. As shown in this figure, with the assistance of homography-guided image warping, the extracted features gradually converge into consistency during recurrence, and hence boosting the homography estimation accuracy. Along with the network recurrence, the scope of attention mechanism shrinks in a global non-local local manner. This operation is deeply bounded with the homography-guided image warping process and the recurrent framework. At the first iteration, the deformation between the two images is large due to large homography deformation. Long-range attention is needed to better capture the inter correspondence. As the iteration continues, the deformation is continuously reduced, and hence the attention can focus on the local area to better improve the estimation accuracy. Let us see more examples about the self-attention and cross-attention map of RHWF at each iteration. Here we show the performance comparison on the MS COCO dataset. It can be observed that our one-scale RHWF already outperforms other competitors except for two-scale IHN, while two-scale RHWF outperforms all others with a large gap. We conduct the evaluation on 4x and 8x cross-resolution MS COCO, which is vital for multi-scale gigapixel photography. It is observed that RHWF ranks top in both scenarios and is significantly more robust under the 8x resolution gap. We further conduct the evaluation on the cross-modal datasets. Google Earth contains image pairs across different seasons, and Google Map the image pairs cropped from satellite images and their corresponding map images. Our RHWF outperformed the competitors. Here we display an example of the iterative homography estimation process of IHN and RHWF on the Google Map dataset. It is observed that RHWF exceeds IHN at the third iteration, and RHWF continues to reduce mesas obviously with more iterations. We conduct the ablation study of the 1-scale RHWF on MS Coco. The bold setting options are finally employed. It is observed that the proposed homography-guided image warping and attention focusing mechanism yields significant gain in accuracy. We can also find the multi-scale refinement very effective by increasing the accuracy by 97.4%. We conduct the parameter and flops comparison in the first table. It is observed that compared to previous methods, our RHWF owns the least parameter cost, which is reduced by 86.5% and 24.6% compared with previous SOTA Works Local Trans and IHN. In the second table, we compare the flops of models and mesas on MSCOCO with the previous SOTA recurrent methods including IHN, its improved version IHN MOV, and DLKFM. Compared to IHN MOV and DLKFM, the computational costs spent on the homography-guided warping in RHWF are much more effective. We also take the RHWF of the recurrent time 3, fewer flops, namely RHWF3, which outperforms IHN MOV and DLKFM. In a word, in this work, we have proposed a novel recurrent homography estimation framework, named RHWF. RHWF absorbs the homography-guided image warping and the focus former, which facilitate the homography estimation by enhancing the feature consistency and capturing the inter-corresponding information in a global non-local local manner, into the recurrent framework. Experimentally, RHWF outperforms previous methods by a large gap with fewer parameters. The computation cost is raised by the homography-guided image warping and attention operation, which is the limitation of our proposed framework. Thanks for watching.